Let's discuss in detail the first step in the LTL model checking algorithm. Let's first answer the question of what type of automata to use. This will be a form of non-deterministic finite automata, but operating on infinite rather than finite words. Namely, we will work with generalized non-deterministic Buki automata, GNBAs for short. A GNBA, OT, is a 5-tuple consisting of a finite set sigma, called the alphabet, and whose elements are called letters. Of course, they don't have to be actual letters, we just call them letters. A finite set of states Q. A subset I of Q of initial states. A ternary relation between states, letters and states, called the transition relation. We write Q arrow A Q prime for the fact that the triple Q A Q prime is in the transition relation. This is the usual notation for automata. The fifth component, calligraphic F, is a subset of the power set of Q, which means it is a set of sets of states. Its elements, which are sets of states, are called accepting sets. This component so far should be familiar to you from non-deterministic finite automata, except that we have a set of initial states rather than just one initial state. And the set of final states from non-deterministic finite automata has been replaced here with a set of sets of states. And we don't say final, but use the term accepting. This is because, as we'll see next, we work with infinite words. And the idea is that, while running an infinite word through the automaton, we do not stop, as no final states, but must visit accepting states infinitely often. So words for us are always infinite. What we call a word, W, is an infinite sequence of letters, x0, x1, x2, and so on. The way GNBAs interact with words is via so-called runs. These are infinite sequences of states, such that the first state in the sequence is initial, and any consecutive states in the sequence transit via the given word's letters. In symbols, if we write Q0, Q1, Q2, and so on for the infinite sequence, we have that Q0 is an element of I, and Qi transits via xi to Qi plus 1 for each I. Moreover, a run Q0, Q1, Q2, and so on is said to be accepting if it visits infinitely often all the accepting sets. More precisely, for all f in calligraphic F, we have that the set of time points I whose corresponding state Qi is in F is infinite. So this set is infinite. And the word is said to be accepted by the automaton OT if there is a run for it in OT. Finally, the language accepted by OT is a set of words accepted by OT. Again, as you can see, the notion of accepting a word and the notion of accepted language are similar to those for finite automata, just that they are adapted to work with infinite words. In particular, acceptance requires visiting each of the accepting sets infinitely often. Here's an example of a GNBA. The alphabet sigma has two letters, X and Y. There are three states, Q0, Q1, and Q2, of which one is initial, namely Q0. There is only one accepting set, the singleton set Q2. Note that calligraphic F is the set of all accepting sets. In our example, only one, which is itself a one-element set. There are 5 elements in the transition relation, which are triples: state, letter, state. We can depict most of this GNBA pictorially, as shown here. The 5 transitions are drawn as usual, as arrows between states labeled with letters. Initial states, here only Q0, can be marked with a short arrow coming into the state from nowhere. So this marks an initial state graphically. I said that we can depict most, though not all, of this structure because the figure does not exactly show the calligraphic F component. It does mark Q2 with double circle to show that Q2 belongs to an accepting set. But calligraphic F really needs to be shown separately, since it is not just a set of states, but a set of sets of states. Note that the acceptance condition for a run, which in general says that all the accepting states must be visited infinitely often, in this example becomes the state Q2 must be visited infinitely often. Let's now consider some examples and non-examples of runs and accepting runs. The word that just repeats the letter X infinitely, written like this X to the infinite, has a run, namely Q0 followed by Q1 repeated infinitely. However, this run is not accepted. This run is not accepting because it does not contain Q2, not even once, let alone an infinite number of times as required for an accepting run. On the other hand, the word consisting of the letter X followed by an infinite number of y's, written x, y to the infinity, has an accepting run, namely Q0, Q1, Q2, infinitely. Now, the word x, then 2 times y, then infinite x, has a run. For example, Q0, Q1, Q2, then back to Q1, and Q1 infinitely. But this run is not accepting. It visits Q2, but only once, hence not infinitely often. Okay, so the run is Q0, Q1, Q2, back to Q1, and then Q1 infinitely. This one does not visit Q2 infinitely often. It is also easy to see that the word y infinitely has no run, since there is no way to start in Q0 with a y. Also, x, y, x infinitely has no run. If we start in Q0 and try to find a run for it, we make it to Q1, then to Q2, but then we get stuck because we have no x transition in Q2. Okay, how about the word consisting of the letter X followed by the sequence X and 2 Ys repeated infinitely? Does it have an accepting run? Please pause the video and think about this. Okay, time's up. Yes, it does. Here is a run. Q0, Q1, Q2, then 2 times Q1 and Q2 repeated infinitely. So 2 times Q1 and Q2, 2 times Q1 and Q2, and so on. Why is run accepting? Because it does visit Q2 infinitely often. More precisely, it visits Q2 every 3 steps. Again, the run is going like this, going like this. So it keeps visiting Q2, which makes it an accepting run. So the language accepted by this automaton contains the words x, y infinitely, x, x, 2 y's infinitely, but does not contain the words x infinitely, x, y2, x infinitely, y infinitely, and x, y, x infinitely. Note that the fact that a particular run for a word is not accepting does not necessarily mean that the word itself is not accepted. The word might well have another run, which might be accepting. But in this case, these words that for which we have shown that they have that particular run is not accepting, x infinitely, and x, y, 2, x infinitely, they turn out not to have any accepting run. So they turn out not to be in the language, as you can check for yourselves. One can actually see that there are two types of words that have accepting runs, which allows us to fully describe the accepted language. The first type starts with x and alternates blocks of x with blocks of y for a while. So it keeps alternating blocks of x with blocks of y, and at some point it settles for y infinitely. This is expressed mathematically here. A number of alternations followed by y infinitely. The second type, again, starts in the initial state. So starts with an x and alternates, again, blocks of y, blocks of x with blocks of y. But in this case, alternation goes on forever, so it does not settle to y infinitely. This is expressed mathematically here. We have this alternation that never stops. Here are two homework exercises that will help you become familiar with the notions of runs, accepted words, and accepted language for a GNBA. You are given a different GNBA. Note in particular that now there are two accepting sets. The singleton Q1 set and the singleton Q2 set. So in this case, a run is accepting if both Q1 and Q2 appear in it infinitely often. Again, this follows by instantiating the general definition of what an accepting run is to this particular case. We have two accepting sets. Okay, so these are the two accepting sets. And both of these need to be visited infinitely often, which means their only elements, Q1 and Q2, need to be visited infinitely often. You are given some words and you are asked if they have runs. So the question is if these words have runs in this automaton and if the runs are accepting, if they have accepting runs. Also, you are asked to try to describe the language accepted by the automaton, like we did on the previous for the previous example. The second exercise asks the same questions for a GNBI that is slightly different from the previous one, where the difference, shown in brown, affects the accepting sets only. We no longer have two singleton accepting sets, but only one accepting set that has two elements, Q1 and Q2. Now, the accepting run condition, which requires visiting the accepting sets here just one infinitely often, means, in our case, having either Q1 or Q2 appear in it infinitely often. So not both of them have to appear infinitely often, but at least one of them has to appear infinitely often for the run to be accepted. This variation should further help you understand how the set of accepting sets influences the notion of accepting run, and ultimately that of accepting of the automaton accepting a word. These notions are quite subtle, so please spend some time with them and ask me questions if necessary.